So, hello everybody. Today we start the next chapter. This is chapter 4 about linear operators and their properties. So we start from the very beginning with all the definitions. And the first topic is just the definitions, norm, and continuity of operators and their basic properties. So definition for 1, so let X and Y be two norm space with respectively norms on X and Y. We consider always norm space over a field K, which is either real numbers or complex numbers. So a mapping A from X to Y is called linear or a linear operator if we have the following identity, that A applied to a linear combination of vectors is a linear combination of application.
Проаналізувати і поговорити. Я буду про це говорити з Тарасом тоді.
Hello. Could you please mute yourself? Okay. So linear operator is a linear or linear mapping. This is a mapping which satisfies this property for all vectors in X and all scalars in our field. If, moreover, this space is just the field K itself, then this A is called a linear functional. The operator norm of a linear operator A from X to Y is defined via the following identity. So the norm, so the operator norm, I will only denote it as just norm without this word op. So the operator norm is the supremum over all x's in the unit ball around 0 in the space X. And we take here supremum of norms of applications A to X, norm of course in Y. In particular, in the same way as here, and in this special case, we define the norm of a linear functional. It is again the same supremum, but now instead of here, we have just an absolute value of the application of our functional to the point X from the closed unit ball. In both cases, closed unit ball. Okay, so I hope that this all is actually known for you, but let us just discuss different forms of this definition. Yes, but before, a linear operator A is called bounded if the norm of the operator norm of this mapping is finite. That is, so since the norm is defined like this, so it's supremum of all these guys over the closed unit ball. This means that the image of the closed unit ball under this mapping A is a bounded set in this space. Yeah, so it's a bounded set which lives in this space inside the ball of radius norm A and center in 0. Okay, so now different formulations of the norm, different formulas for calculating the norm. So this is the definition, the official definition. So a norm of A is equal to supremum over the closed unit ball of such things. But it is the same as supremum over all elements of X which are not 0 of such fractions. And it is also the same as supremum over the unit sphere of such guys. So compare this supremum and this supremum. And it is also the same as infimum over all constants C, non-negative, such that we have such inequality for all x's in X. So let us discuss all these things a little bit in more details. In particular, let us compare this guy and this guy. So in one hand, supremum over the unit ball, the closed unit ball of something. It is, of course, not smaller than supremum over just a part of this unit ball, namely only the boundary, so unit sphere. Yeah, agree? So this is a bigger set than this one. That's why supremum over a bigger set is not smaller than supremum over its subset. This is in one hand. On the other hand, for any, okay, this is so to say one direction. On the other hand, for any x in this unit ball, not bounded but open, there exists another element x tilde, which belongs to the unit sphere, such that x is equal to alpha x tilde, where my alpha belongs to the interval from 0 to 1, not 0 and not 1. Hence, by linearity of the mapping A, the norm AX in Y is the same as the norm of alpha x tilde in Y. And now we use linearity and properties of the norm. This is just alpha, because alpha is here, non-negative. Alpha times the norm of AX tilde in Y. And this is something which is smaller than norm of AX tilde in Y. And hence we see that the supremum over this set is actually the same as supremum of this smaller set. Yeah, and you agree, or should I write down something more?
Please write something more.
Yeah, so from this follows that supremum over the whole closed ball of this stuff is actually supremum over the boundary of this ball. So this supremum is not bigger than this supremum, but actually all what happens inside the ball is not bigger than everything what happens on the boundary. So this thing shows that this supremum is the same as this supremum. Are you agree or ask questions, because I don't know what else should I say?
Well, I think it's clear. Thanks.
Okay. Well, now let us discuss this stuff, the identity with this number. So let me write down it here. Sorry, I have not too much place. So for any x in x, which is not 0, x is not 0, 0 element, 0 vector of our space x, we have that x over its norm in x. This is, of course, an element of a unit sphere. That is, this is the element of this boundary. Hence, by linearity of operator A, what do we have? Supremum over norm x not equal to 0, norm ax in y over norm x in x. This is just, so what should I do? Supremum, so what do I do? So using the properties of norm, this is just a number. So I can put it inside the norm, so just here. And then using again the linear, so this is the property of norm. So constant can be pulled outside or in, positive constant. And then I use linearity of A, so this constant can be put even here. So this is supremum, and here we have A, and here x over norm of x, everything in y. Again, the same supremum. Yes, but this is just with change of notation. This is supremum over, okay, x tilde norm is equal to 1, supremum of A x tilde probably tilde, not tilde, let us call it somehow. Okay, so this is my new x tilde. So we have shown that this guy is the same as this guy. Because of course, when x is equal to 0, A is a linear mapping. Yes, A of 0 is 0. This we should pay into account. But for all x satisfying this condition, these things belong to this space. And vice versa, by rescaling, such things can be mapped to such things. Okay, so I hope it's clear that we have now shown that this stuff shows that the norm is the same as such supremum. Okay, so what happens here? If we consider such C, any C which satisfies this condition, let me write down somewhere, probably here. So consider some C such that norm of AX in Y is smaller or equal C times norm of X in X, and this holds for all X in X. From this follows that the norm of AX in Y over norm of X in X is smaller or equal to C for all X which are not the zero vector. So whose norm is not 0. From this we see, taking into account this definition of the norm, that since this holds for all x's, then supremum over all x's also satisfies this inequality, and hence the norm of A is smaller or equal to C. For any C satisfying this condition. But this means that the norm of A is just the infimum over such C. Yeah, so the same what is written here. Why? Because if the norm of A is strictly smaller than such infimum, then there exists another C tilde, also positive, which lies in between the norm of A and such infimum, but this then contradicts to the definition of infimum. Because for such C tilde also this inequality would hold due to the definition of norm, due to the definition of supremum. Okay, I hope that it was more or less clear. So we have presented different versions how one can calculate the norm. So this is the official definitions. All other things are also sometimes helpful. In particular, we have, I will write here, hence, we know that the following inequality holds. AX, the norm of AX in Y is smaller or equal to the norm of A times the norm of X. And this holds for any X in X. Just look here. And this is a convenient inequality which one sometimes uses. Are there any questions, comments? Okay, so let us go further. So second part of this remark, so we have free norm space, a mapping A from Y to Z, and the mapping B from X to Y. Then we can consider the composition AB, this will be a composition from X to Z. So the statement is that if A and B are bounded linear operators, then their composition is again a bounded linear operator, and we have the following inequality. Yeah, so it's a home task or exercise to show that this is so, but yes, you can use this and definition of norm, of operator norm to check it. Please pay attention that we have here smaller or equal. We cannot replace it by equal, so there are counter example. I mean, one can construct a lot of counter examples themselves yourself. The idea is as follows. So let me write down. Probably I will write down like this. There are cases with a norm of AB is strictly smaller than norm of A times norm of B. So one can take A, which is not zero operator, B, which is not zero operator, but such that their composition is a zero operator. Then on the left-hand side, you have zero, and here you have something strictly positive. For example, one can consider a Hilbert space and projections, orthogonal projections onto different subspaces which are orthogonal to each other. Yeah, so a composition of two orthogonal projections on two different orthogonal spaces, subspaces which are orthogonal to each other, will lead to a zero operator. Okay, is everything clear?
Yes.
Okay. So let us go further. Remark. So this is the notation for the set of all bounded linear operators from X to Y. X and Y are two normed spaces. So the statement is that this set is itself a normed space endowed with the operator norm. So argumentation is quite standard, so let us see it. So we show that this set is a linear space. So if we have two bounded linear operators, so this L for linear, but also bounded operators. So if we have two linear bounded operators, then their linear combination is again a linear operator. And since A and B are bounded, these sets are bounded sets in Y. And hence, this operator maps this closed unit ball onto this set due to linearity. And this set is also bounded in Y for any fixed alpha and beta in K. One can check it very, very easily. Since this set is bounded and this set is bounded, and one can prove that their linear combination is again a bounded set. Hence, we have shown that this linear combination of operators again belongs to this set, and hence this set is a linear space. Now concerning the norm space, so we have to show that the operator norm is really a norm. So before it was just a definition that we call, so we define an object like this, and we call this object the operator norm. Now let us show that it's really a norm. So since X is a norm space, so this norm in X, this is a norm. A norm in Y is also a norm. This we know. So using, sorry, this is a typo, so here should be Y. Yeah, so norm in Y is really a norm. That's why we can use triangle inequality, and hence the norm of this object is smaller or equal than, so the norm of sum. So here we have AX plus BX. So the norm of this sum is smaller or equal than the sum of the norms. And also, again, by the property of this norm, so we can pull out scalars outside with absolute value. So this also holds, since this guy is really a true norm. Hence, what do we have? We calculate the norm of operator norm of this operator a plus b. This is by definition. And now we use this triangle inequality. So this is smaller or equal than supremum. And here we have sum of norms. So supremum of a sum is smaller or equal than sum of supremums. That's why we have separated two supremums. But then by definition, this guy is just the norm of A and this guy is just the norm of B. And hence what we have the triangle inequality for the operator norm. This is one of the properties which is needed for an object to be a norm. Next property, if we consider alpha times an operator A, so operator norm of this object by definition is the object like this. But here we have the real norm in Y. So we can pull out alpha with absolute value. So first here, but then absolute value of alpha is a positive number. So supremum of absolute value of alpha times something is the same as alpha, absolute value of alpha times supremum. So we can pull it out also here. But then this is the definition of norm of A, so we have this identity. Hence, we have shown that this holds. Yeah, and obviously, since we have linear mappings, A of 0 is equal to 0 for all mappings. But this is not what I wanted to say. I wanted to say that, okay, looking at the definition of what is the operator norm, we see that operator norm of A is equal to 0 if and only if the operator is a 0 operator. That is, A of x is equal to 0 in Y for any x in X. Hence, all the properties which are required for the norm, they are satisfied. And hence, we really have, hence the operator norm is really a norm. And hence, this set is a normed space. Now, next, so first of all, is everything clear? Do you have questions? Okay, so we go further. Some properties of operator norm. So we have two normed spaces and a linear mapping. The following statements are equivalent. A is a bounded linear operator. A is a continuous operator. A is continuous at just some point x0 in X. So let us show these statements. Let us prove it. So first of all, of course, we will have two. Property 2, this implies property 3, obvious. Let us show that 1 implies 2. So let A be bounded. BDD means bounded. That is, the norm of A is finite. Then, by remark 4.2, part 1, the norm of AX1 minus AX2, the norm in Y. This is the norm of A applied to x1 minus x2 in Y, norm in Y. This is smaller or equal to the norm, the operator norm of A times the norm of this vector x1 minus x2, the norm in X. And this holds for any x1, x2 in X. And this means that A is Lipschitz. So this is the Lipschitz constant of this mapping A. And we have also discussed that if the mapping is Lipschitz, then it is continuous. Okay. Now let us show that 3 implies 1. So let A be continuous at some point x0, just in one point probably. This is what the all information we have. Since A is linear, we have for A of x is equal to minus A applied to x0 minus x plus A of x0. We show that A is continuous at x equal to 0. So sometimes I denote this 0 as 0 element in the space X, but let me ignore this subscript in the sequel. Okay, so what we want to show. So we consider a sequence Xn which converges to 0 when n tends to infinity, and we want, this is what we want. Something happens. This is what we want. To show that A of Xn converges to A of 0, but this is 0 because we have a linear mapping. So let us show it. A of Xn is equal to, now I use this identity, which holds for any x, hence for Xn as well. So this is minus A, and here x0 minus Xn plus A of Xn, or x0, sorry. But this guy converges to x0. And under our assumption, A is continuous at x0. Hence, so this thing converges to, okay, minus is remains A of x0 by assumption. Okay, hence this stuff converges to minus A of the x0 plus A of x0. This is just 0. And this is A of 0. So we have shown this. Now assume that this statement is not true. That is, the operator A is unbounded. That is, its norm, operator norm is infinity. Then there exists a sequence of vectors Xn satisfying the following properties. So they all live in the unit sphere. but norm of A applied to xn is bigger or equal to n. If we cannot find, if it is not possible to choose such a sequence, then we cannot. So better to say as follows. We assume that the norm is equal to infinity. The norm is a supremum of such things over a unit sphere. So by definition of infinity, there exists a sequence which goes to this supremum. That's why we can construct such sequence xn with such properties. Okay, but what do we have then? Then we have that the vectors k1 over n times xn, this sequence converges to 0. But the norm of A applied to these elements of this sequence, what is it? We use the properties of the norm. This is 1 over n norm of AXN. And this should be bigger or equal to 1, and hence this does not converge to 0. And this is contradiction to the following statement. Yeah, so this we have already shown. This is not a question mark anymore, but this is a statement that under our assumption. So we have shown, so what has happened here? So we have this, that A is continuous at some point x0. After that, we have shown that this A is continuous at 0, namely that this holds. This we have shown. And now using this continuity at 0, we show that if we assume that the statement 1 is wrong, that is, the norm is infinity, then the continuity at 0 is violated. Yeah, contradiction, because we have constructed the sequence which converges to 0, but A applied to this sequence does not converge to 0. Okay, so everything is proved. Are there any questions?
So it's not just continuous, but Lipschitz also.
Yes.
Mhm.
Mhm. Okay, so please remember these equivalent statements, and we go further. So I was very, how to say, I have saved a lot of space. Okay, corollary from this statement. So let x and y be normed spaces over K, A be a linear operator. A is continuous if and only if for any sequence xn in X which tends to 0, the set of the images, so this is a sequence in Y, this sequence is bounded. This is also a kind of a useful criteria. So let me discuss the proof. So in this direction, that is, if A is linear, then that's true. Sorry, if A is continuous, then this is true. Because if A is continuous, it is continuous also in 0, and then for any xn tending to 0, A of xn also tends to 0. And since this is a convergent sequence, it is bounded. So this direction is obvious. Opposite direction. So assume that this holds, but A is not continuous, and hence A is not bounded. Yeah, so please pay attention that bounded and continuous is the same for linear operators. So assume that this holds, but this is not true. So assume that the norm of A is equal to infinity. Hence, by definition of supremum, there exists a sequence xn in X such that all elements live in the unit sphere and A of xn in Y tends to infinity. Yeah, so again, so the norm is the supremum over such set of such things, supremums of such things over such set. So hence there exists a sequence which how to say approximate this supremum. So if we have this, then we consider another sequence which is just xn over square root of norm of A of xn in Y. Okay, so this is a bounded sequence, and this guy tends to infinity. It's a scalar. So 1 over the square root of this real valued sequence, it is something which tends to infinity. Then when we divide on it, so this tends to 0. Hence, what we have that this guy tends to 0 when n tends to infinity. But if we consider norm of A xn tilde in Y, this is just square root of norm of A xn. And this tends to infinity. And this is a contradiction with continuity. So contradiction with this condition. This was the assumption. Oh, sorry. Let me write down it like this, that hence this set AXN tilde is not bounded in Y. And this is contradiction with our assumption. Okay. Is everything clear?
Yes.
Okay, so please remember, so if we have a linear operator, it is bounded if and only if it is continuous. And it is enough to check continuity at only one point. And this is also a nice criterion of continuity or boundness. Okay, so let us go further. So let X be a norm space whose dimensions or Hamilton dimension is infinity. Then there exists a linear functional which is not continuous. So in linear algebra, in finite dimensional space, of course, all linear functionals are continuous mappings. But this is not the case when we consider this general situation. So counterexample. So let V lambda be a Hamilton basis of this space, norm space whose dimension is infinity. So if we have, so each vector space has a Hamilton basis. So if we have a Hamilton basis, we can normalize all the vectors. So we can construct a new Hamilton basis which satisfies this assumption. Okay, since we know this, we know that this set lambda is an infinite set. So we have infinitely many vectors in Hamilton basis. we don't know, since this is not a Banach space, it's not a complete space, we don't know if this Hamilton is countable or uncountable. For in the case of complete, so in the case of Banach space, we can use the theorem of Baer to show that Hamilton basis in this situation is uncountable. But for us, it is enough to know that the set lambda is infinite. So this word is actually choose. So I have lost H. Choose a countable subset of vectors in this Hamilton basis. Since we don't know if lambda is countable or not, just choose a countable subset within this Hamilton basis. Now we define the functional L in the following way. So L applied to the vector v lambda n from this sequence. V lambda L of v lambda n is just n. And for all other vectors from the Hamilton basis which are not here, not in this sequence, we just put L of such vector basis vector is equal to 0. Okay, so this is how we defined L on the whole set of vectors from the Hamilton basis. But now we may extend L onto the whole space X by linearity. What do I mean? I mean that for any X in our space, big X, there exists a finite linear combination. There exists unique. So there exists a unique representation. X is equal to alpha 1 E1, no, not E, V lambda. Okay, V1 plus etc. alpha n Vn, where these vectors are from the Hamilton basis, and here are some coordinates from this field. Then this is the unique representation, and the linear combination is finite. And hence, since L is defined on all vector elements, so we can define by linearity L of X by just putting alpha L of V plus etc. plus alpha n L of Vn. So I hope it's clear how to define L everywhere by linearity. So what do we have then? We have then a linear function on the whole space X, which is unbounded because we have unit vectors, and L over such particular unit vectors is growing. So if we consider supremum of such things over all vectors from the unit sphere, it will be infinity. And hence, since the norm, so due to this definition, we see that norm of L, which is just supremum over all X equal to 1, and here absolute value, L of X, this is just infinity, yeah, because of these things. Hence, L is not bounded, and hence it is not continuous. But this means also that it is discontinuous everywhere, because we know that continuity only in one point means continuity everywhere. So if we have a linear mapping, linear operator, if it is bounded, it is continuous everywhere. But if it is not bounded, it is discontinuous everywhere. And this is a construction of such a guy. Other questions? Okay, so hopefully everything is clear. And let us go further. So definition. Let X be a norm space over some field K. The space X star, so let me make it, so I have two different stars. This is one version of star, and this is another version of star. I will clarify why I have chosen such a notation. So the space X star of all linear functionals on X is called the algebraic dual space to X. And now the space X star with such like snowflake. So the space X star, this notation is the notation for the space of all continuous linear functionals, or equivalently of all bounded linear functionals on X. So from X to the field K. And this space is called the topological dual space to X. So we are interested in this course in this space, not in this space. So historically, probably first would be the algebraic dual, and it was X star, and then the topological dual. So let me make a remark. Okay, so if we are in the finite dimensional situation, these two things are the same. That's why both are stars, X stars. But as we have seen already from the previous remark, in the infinite dimensional situation, there are some linear functionals which are not continuous. So this is a bigger space than this one. And so there are different notations for this space. So like classical notation from functional analysis is X star for this topological dual. Also, people who working in the theory of PDEs, partial differential equations, they use this notation, so prime, X prime. So I will use X star in my lectures because this is exactly the star which has the link to Weak star topology and Weak star convergence. So this star in the names of topologies, they are due to this star. That's why we will use this notation, but please pay attention that also this one is standard notation. And yes, so this is the object of our investigation. This is just for information. I don't think we will really use it. That's why it also X star, but a little bit different star. Okay, so as I have already said, if X has finite dimension, then both stars are the same. So X star is the same for algebraic and topological dual. If dimension X is infinity, then topological dual is of course a subset of algebraical dual, but is strictly smaller. So this is an important space, and it will be discussed within the lecture course. Now some examples of bounded linear functionals, that is elements of X star with this snowflake star. Okay, so we consider as the norm space the space of continuous functions defined on the segments from 0 to 1 with supremum norm. This is the definition of the norm. So let us define the functional L, so the mapping from X to numbers, to K, which acts as follows. So L applied to F is just F evaluated at point 0. Then the norm of L is supremum over the unit sphere, such absolute values. And this is obviously smaller or equal to 1. Furthermore, if we consider a function which is identically 1, this is of course element of this space, and it satisfies this assumption, then L of F is equal to 1, and hence so this supremum is attained. That is, this upper bound is attained. That is, the norm of L is just 1. Of course, L is a linear mapping. Hopefully it is clear. And we see that it is a bounded linear mapping, or continuous linear mapping. Everything is clear?
Yes.
Okay. Another example, let us consider, so the same space, consider the following function g. It is not a continuous function, it's a discontinuous function. It's -1 on the half of interval and +1 on the other half of interval. But now let us consider the mapping from x to k, which does the following. So L of f, this is this integral from 0 to 1. We integrate f, element of our space, with this, so to say, weight. This is the weight. Then what do we have? So absolute value of L applied, so at the point f, this is this integral. Absolute value of the integral is smaller or equal than integral of absolute value. Now, absolute value of this guy is just 1. So we can, so this is just 1, so we can forget about it. And then this guy is smaller or equal than norm of f, supremum norm, times integral from 0 to 1 dt, and this is just 1. Hence, we have this estimate. And from this estimate, we see that the norm of this mapping is smaller or equal to 1. Of course, again, this mapping is linear with respect to f due to linearity of integral. So let us check that the norm of L is actually equal to equal to 1. So in this case, we just presented an element f such that L applied to f is exactly this, is exactly 1. It was in this case. In this situation, it is not possible to find such an element. But for any epsilon positive, there exists an element in our space which belongs to our unit ball, closed unit ball, and such that L applied to this element takes the value 1 minus epsilon. So this we can construct in the following way. So this is the function gt, so the weight, which is used in the integral. This is this function. Of course, this is not the element of our space, x, but we can approximate it by some continuous functions, which are elements of our x, and they act as follows. So we take some epsilon neighborhood of 0.1/2. So that is, this distance is epsilon. So outside this interval, our function f takes values -1 here and 1 here. And inside this interval, this function is continuous and just connect these two values. Then we see that this product f and g is non-negative on the whole interval on. Moreover, this product is just 1 outside this segment, so here. That's why if we consider L applied to this f, this is just integral from 0 to 1 f times g dt. This is so this is non-negative. That's why this integral over the whole segment is not smaller, or actually bigger, but this okay, bigger than the if we only calculate the integral over this sub part of the interval from 0 to 1. So this is here. So instead of integrating over the whole 0, 1, we integrate only here. But here, this product is just equal to 1. Hence, this integral is just the length of this interval from here to here. And this is 1 minus epsilon. And of course, we can make epsilon arbitrarily small. So what do we have finally? We have that the norm, which is supremum, supremum. So in one hand, the norm is smaller or equal to 1, but on the other hand, it can be, so there are elements such that L applied to F is arbitrarily close to 1. Hence, the norm is exactly 1. So the norm is exactly 1. However, there is no element F in our space such that The functional L applied to this element is just this norm. So the supremum is not attained. So supremum is not maximum. Maximum is not attained over a closed unit ball or a closed unit sphere. But please pay attention that this is an infinite dimensional space, normed space. And this set, so a closed unit ball, it is not a compact in any infinite dimensional space. And hence there is no contradiction. I mean, we know that if we have a continuous mapping over a compact, it should attain its maximum value, global maximum. But this closed unit ball is not a compact. And we should not expect that this supremum in the definition of operator norm or normal functional analysis is actually attained on some element. So in this case, it was attained. In this case, it is not attained. Okay, other questions? Okay, so seemingly everything is totally clear, I hope. Yeah?
Yes.
Okay, then we go further. And continuous operators may be uniquely extended on the closure of their original domain of definition. Namely, there is the theorem, let X be a norm space over K, let D be a dense subspace of X, let Y be a Banach space over K, and L a bounded linear operator from this norm space into this Banach space. Then there exists the unique extension of A to a continuous linear operator, not from D, but from the whole space X. And the norm of this extension in this new operator space is the same as the norm of the original operator in the original operator space. So let me show the proof. Uniqueness. So uniqueness of extension. So let A bar be an extension, so some extension of A. Then for any X from big X, there exists a sequence Xn from D with Xn tending to X. This is because D is a dense subspace of X. Okay. Then A bar of X by continuity is a limit of n tending to infinity, A bar of Xn. But since A bar is an extension of A, so what does mean extension? This means that A bar restricted to D is exactly A. This is the extension. So we have this because Xn belongs to D. So, so you see, whatever extension we take, at any point, it takes the same value. One can show that this value does not depend on the approximating sequence xn, and hence this gives us the uniqueness of A of x. So A bar is unique by properties of limit. Okay, now we prove existence of such an extension. Again, let x be a point in x, and then xn be approximating sequence from D. From this, we see that so if xn is a convergent sequence, then this is also a Cauchy sequence. But then A of xn is a Cauchy sequence in Y, since A is Lipschitz, yes? We have shown it already, mentioned it already. Okay, norm of xn, A of xn minus A of xm is smaller or equal than norm of A times norm of xn minus xm. Which continuous mapping is Lipschitz. Hence, since this is a convergent sequence, it is a Cauchy sequence, hence this thing tends to 0 when n and m tend to infinity. And hence the same is true for such a sequence. Okay, but everything happens in a Banach space Y. And hence, the space is complete, and hence any Cauchy sequence has a limit. So since Y is complete, so is Banach space and hence complete, there exists the limit of A of xn, and this limit we call A bar of x. Then, and this is like an exercise, this definition of A bar does not depend on the choice of approximating sequence. And A is linear and continuous. It's exercise. Okay. So once again, so if we have a linear mapping from one, okay, so D, it can be considered as a normed space itself, but nevertheless, so if we have a dense subset in some bigger normed space, then we can extend any bounded linear operator or continuous linear operator from D onto the whole X by a very natural way. Well, this results also known as BLT theorem, BLT for bounded linear transformation. Yes. And it is this result is helpful in applications because sometimes it's very convenient to consider an operator defined not on the whole X but on a dense subspace of, like, say, good elements. For example, like we consider differential operator on smooth functions, which are just a subspace of like L2, for example. And we consider operators on a nice subspace where this operator is given explicitly, and we investigate it there, but then we can make conclusions about the corresponding operator on the whole space. Okay, let us go further. So this was one result. So one more result. So theorem 10, let X be a norm space, let Y be a Banach space, then the space of all bounded linear operators from X and Y endowed with the operator norm is complete. That is, it is a Banach space. We have clarified that this guy is a norm space, but if Y is a Banach space, then this guy is a complete norm space. That is a Banach space. So in particular, if we consider Y equal to K is our field of scalars, this guy is a Banach space. Yes, in this situation. And hence we get that the topological dual of any norm space X is complete. We don't care if X is complete itself, but anyway, since K is complete, due to this theorem, the topological dual is complete. Okay, so let us prove it. I would say that the proof is again a standard one, but it does not mean that we should not make the standard proofs. Let us do it sufficiently fast. So let AN be a Cauchy sequence in this space L of XY. For any X in this space X, the sequence AN applied to X is then a Cauchy sequence in our field K. Sorry, not in K, in where? In Y. In Y. And now we know that Y is the Banach space. Again, so this is a Cauchy sequence by the same argument which we have used already. So norm AXN minus, ANX minus AMX norm in Y is smaller or equal norm of AN minus AM times norm of X in X. Okay. Yes, so since we have a Cauchy sequence AN, so this stuff tends to 0 when n and m tends to infinity. Hence, the left-hand side also tends to 0, and hence we have a Cauchy sequence in Y. But Y is a Banach space, so each Cauchy sequence has a limit. So for any X in X, there exists a limit, n tends to infinity, an of X, and we denote this limit as AX. This is just the notation for the limit, but hence we have a mapping. We have a mapping A from X to Y. So this mapping is defined on the whole X because of this. And it is linear. By properties of limits. Yeah, by this definition. Since these guys are linear, then A is also linear. So is it clear, or should I clarify it in more details?
I think it's enough.
Okay. Now we show that this operator A is not only a linear mapping, but also a bounded mapping or continuous mapping. So we show that A belongs to this space. How we show it? So for any epsilon positive, there exists n natural number such that for all n and m bigger or equal to this n. So we use the triangle inequality for the operator norm. We have the following. So operator norm of an minus operator norm of am, absolute value of this difference is smaller or equal than the norm of an minus am. So this is triangle inequality for the operator norm. But this is smaller than epsilon because IM is a Cauchy sequence here. So what does it mean? This means that the norm of IN, such sequence of norms, is a Cauchy sequence in our field. But actually, since all norms are non-negative, it's even here. But it doesn't matter. But we know that our field K, in particular R, is a complete space. Hence, each Cauchy sequence has a limit. That is, there exists a constant. Okay, each Cauchy sequence has a limit, but in particular, it is bounded sequence. Each Cauchy sequence has a limit, so it is a convergent sequence, and each convergent sequence is bounded. That is, there exists a constant C such that operator norm of an is smaller or equal than this C, and this holds for any n. Hence, what do we have? Norm of ax, norm in y. This is a limit, n tends to infinity, norm of anx, yes, due to this, and due to the fact that the norm is a continuous mapping in the topology generated by itself. But this is smaller or equal than supremum over all n anx in y, but this is smaller or equal than supremum over n in n of operator norm of an times norm of x. And now this supremum is smaller or equal than c. So what do we have? There exists c such that ax is smaller or equal than c times norm x. Hence, by the remark, hence we have that the norm is finite. That is, A is a bounded linear operator, and the norm of A is smaller or equal than this C. But this is not all. So, so what do we have shown? We have shown that there exists a bounded linear operator A, which is a pointwise limit of our Cauchy sequence of operators. But we don't need pointwise limit. We need a limit in the operator norm. So this is what we have to show still, that this guy, so this guy A, defined in this way, it is a candidate of being a limit of the Cauchy sequence in this space. So let us show that this candidate is actually the limit. So I have to go to the next slide. May I?
Okay.
Okay, so we show the following. So we have that the norm of operator norm of an minus n, a, tends to 0 when n tends to infinity, since for any epsilon positive, there exists n, natural number, such that for all x in our space x, with norm of x equal to 1, so elements of unit sphere, we have okay, I will write down holds, which is not a nice English, but we will survive. The following is true. So an x minus am x norm in y is smaller or equal than an minus am times norm of x in x. This is smaller than epsilon. This all we have written already. But what does it mean? Now let us, so in this inequality, let us take the limit when m tends to infinity of this anx minus amx. So since this guy is smaller than epsilon, then such a limit will be smaller or equal than epsilon for any n fixed. But this limit is just norm of anx minus ax, but by definition of a. Yeah, so what we have shown. For any epsilon, there exists n such that this guy is smaller or equal than the epsilon for any n, for any n big enough. But this is exactly means that an tends to a in this operator norm. Wait. Wait. Well, I don't like this conclusion. Because I guess we need something more which we don't know at the moment. So, so let me make as follows. So this is a part of the proof which is not yet complete, actually. But at the moment, I don't want to clarify. So there are some steps which we are not able to clarify yet because we don't know some suitable theorems. So after we learn these theorems, we come back here and we will clarify this final step, okay? So I postpone the part of the proof because because it uses something which I didn't notice, but but now I see that we need something more which we don't know yet. So we postpone this part of the proof. So later. And come back to it. Okay, so home task for all of us. But nevertheless, the statement is true. And actually, so far we have finished so the basic properties of linear operators. Now there are some, so to say, big theorems about more advanced properties of linear operators. And one of these properties is the so-called open mapping theorem. So let us discuss this theorem today. We have not that much time, but still, nevertheless, let us discuss it somehow. So what is it all about? So we are motivated by solving equations of this form. So u is an unknown function and f is a given function. So everything happens in some functional spaces. So the question arises. So let A be a bijective, so bounded linear and bijective operator. Then, of course, in this case, we can find u by applying a to the power minus 1 to the right-hand side. So right-hand side is something known, but what does mean known? This means that it was measured in the lab. So it may have some mistakes. So that's why the natural question arises when this operator a to the power minus 1 is continuous. That is when the solution continuously depends on the right-hand side. That is, if we perturb right-hand side a little bit, because of measurement errors, the error in the solution will be also small. So this is the aim. We have a bijective bounded linear operator when is its inverse continuous. Some consideration. So let us call this inverse by B. So this operator B is a continuous mapping if and only if, by definition of continuous mapping, the pre-image of all open sets are open. So this B is a mapping, my B maps Y to X. So, and this mapping is continuous if for any open element of X, open set in X, its pre-image is an open set here. And now I rewrite these statements in terms of A, and I have this. So inverse is continuous if and only if for any open set in X, its image, not pre-image, but image, is open in Y. So motivated by this problem, by this task, aim, we are interested in mappings A such that they map open sets to open sets. So this gives the definition. A mapping between two metric spaces is called open if it maps open sets to open sets, like here. So we have a mapping A, and it is open if this holds. Okay, note, if F is a bijective mapping and an open mapping, then its inverse is a continuous mapping. This is just exactly our consideration. Quotient. So what is the quotient? So in the definition of a continuous mapping between two topological spaces, so we said that the mapping is continuous if pre-image of any open set is an open set. And we also mentioned that the word open can be replaced by the word closed. That is, a mapping is continuous if the pre-image of any closed set is a closed set. Quotient in the definition of open mapping, it is not possible to replace open by closed because there are open mappings which do not map closed sets into closed sets. So a counterexample. So we consider a mapping F from R to R, which is a projection on the first coordinate. And we consider this set. So since we have here such type of inequalities, one can show that this is a closed set. And one can check that the projection to the first coordinate of this closed set gives us this interval. So this is an open set in R. Hence, you see, we cannot say that the mapping is open if and only if image of any closed set is a closed set. This is not true. This is a counterexample. Okay, so let us go further. Lemma criterion of openness for linear mappings. So let X and Y be norm spaces, A be a linear mapping. The following statements are equivalent. A is an open mapping. For any R positive, the image of an open ball with centrum in zero, with center at 0 and radius R. So the image of an open ball is a neighborhood of a region in Y. That is, there exists a row strictly positive such that the open ball around 0 with radius R in Y is a subset of this set. So this is the statement for any R, and this is the statement that there exists at least one R such that this holds. Okay, so we still have some time, so let me try to prove this lemma. Okay, so first of all, let us see that 3 and 2 are equivalent. 2 is equivalent to 3. So why? So if we have 2, it implies 3, of course. But if we have 3, then by rescaling and linearity of, so rescaling, that is, by the rescaling of the space and linearity of T, we have that, so we can rescale such open ball to any other open ball with any other radius, positive radius. So by rescaling, I mean, X is mapped to some constant times X, positive constant. And linearity of A. And now let me show that 1 implies 2. This is, so what is 1? A is open. What does it mean? That, so this is an open set. And since A is open, that image of open set is an open set. So everything is true due to openness of A and the fact that A of 0, this is 0, since A is linear. And this is, of course, element of A of Px R0. Okay, so since A is open and this ball is an open set, then A of an open set is again an open set which contains 0. So everything is done. Now, the most interesting situation, we show that 2 implies 1. So let U be open. Y is an, sorry. Let me write down here. Y be an element of A of U. And X be an element of U such that A of X is this preliminary chosen point Y. So U is open, hence there exists some radius, positive radius, such that U contains the point X with its R neighborhood. U is open set, X is a point in this U, so there is even a open ball around X, which is inside U. Now we use this assumption 2, that A of this open ball, this is R, it is, of course, a subset of the space Y and is an open set. So let me specify that A of this open ball, due to linearity of A, this is nothing else but A of the open ball with the same radius around 0 plus A of X. I didn't use brackets before. And this is open by our assumption 2. Okay, and hence also its shift also open. So this guy is open. But what does it mean that this guy is open? This means that there exists, so in one hand it is open, on the other hand, so we know that this is open. Using this, there exists a rho positive such that a ball in Y with radius rho around 0 is a subset of A of Bx R0. Yeah, so it's an open set which contains 0. It's a neighborhood of 0 in Y, and hence there is an open ball around 0, which is a subset of this neighborhood of 0 in Y. So what do we have? So let me write down it here. So A of U, it contains A of BRX of X. Yeah, because we have this inclusion. Hence we have this inclusion. But what is it? The right-hand side is equal to A of X. A of X plus A of this BRX0. And it contains a smaller set. So this guy is just Y by our definition of X. And this guy contains, so we use this inclusion. So it contains a smaller set, namely this set. Hence, finally, we have Y plus by rho of 0. But this is by rho of Y. So what do we have finally? U is open. Y is any element of its image. And hence the whole neighborhood of Y is included in this image. This means that A of U is an open set. Yeah? For any U open, its image is an open set, because for any point of inside this image, there is even a neighborhood of this point, which is inside of this set. Hence, A of U is open. And hence A is, okay, hence A is open. That is, one is satisfied. So then this is satisfied.
Excuse me, can you please explain how we can have that A from BRX from 0 is open?
So you mean, so you
quantify
ask why this is open, yes?
even the right from it.
So our assumption is, so we prove that from 2, so 2 implies 1. That is, this is our assumption.
Yes, but in our assumption, we just have that in our ABR0, we have some open ball, but maybe...
No. So the statement is as follows. For any R, the image of open ball is a neighborhood of a region.
So maybe it's in
Open.
the word neighborhood, it is mean by
Open
definition,
set. Not a ball, but not an open ball, but an open set around a region.
okay, so I'm sorry. Okay, so it is just by definition, neighborhood is always open set, yes?
Yes, in my course, yes.
Okay, thank you very much.
In general, when one discusses topological spaces, one can actually even forget about open set, just any set. So a neighborhood of a point is any set such that this point lives in is an internal point of the set. So lives there with some open neighborhood. But it's like something you don't need it actually.
Okay, thank you very much.
Yes, so open neighborhood, yeah. So after this assumption, yes, so this is open then, and then its shift is also an open set, and then everything is clear, I hope. Okay, may I go further? Let us at least see what was supposed to go to be further. Yeah, so some examples. So actually our time is already over. That's why the question, do we want some examples or should I stop right now?
For me, I have to leave, but you can continue. I will see the recording.
Okay, so probably then we should stop now and we will continue on Friday. Okay?
Well, that's also okay. Thank you very much.
Okay.
Thank you very much.
Are there any questions or comments?